Welcome to your online training module, Introduction to Medical Entomology. In this unit, we will explore vector surveillance, focusing on the various sampling methodologies and tools used when implementing a surveillance program to investigate a vector-borne disease outbreak. Before we jump into this unit, Vectorlandia has made significant progress in creating a profile for the country. Now, let's see what steps they will now take to address the outbreak.
Doctors in Vectorlandia confirmed the illness is vector-borne. While final verification is pending, the Vector Control Unit is reviewing its updated surveillance strategy, reviewing inventory of equipment, matching tools with specific vector species, and deciding which tools will best support monitoring programs and population control in affected areas.
Vector surveillance refers to the systematic process of collecting, analyzing, and interpreting information about insects, particularly those that act as disease vectors or agricultural pests. Entomological surveillance plays a central role in vector-borne disease control programs. Through this process, specialists can detect outbreaks at an early stage, track how vector populations change over time and space, monitor whether these vectors are becoming resistant to insecticides, and evaluate how effective current control measures truly are. Identifying where vectors are located and in what numbers is a critical first step in understanding the scale of the outbreak. However, not all vectors behave the same way. Mosquito species, for example, differ in their feeding times, resting habits, and breeding sites. Because of this, a single surveillance tool cannot provide all the answers. Instead, respective tools and collection techniques must be selected based on the biology and behavior of the species under investigation. The BG Sentinel trap attracts Aedes mosquitoes using visual and scent cues. Its dark exterior enhances visual appeal, while a battery-powered fan creates downward airflow that draws host-seeking mosquitoes into a funnel and into a labeled collection bag. Collected specimens are retained for species identification, vector competence analyses, or pathogen screening. Effective deployment requires aligning trap placement with mosquito behavior and environmental conditions. The gravid Aedes traps target ovipositing female Aedes by exploiting their natural egg-laying behavior. Females enter the trap sensing nutrient-rich infused water on the lower chamber to lay their eggs. However, a mesh barrier prevents egg deposition on the water surface and are trapped within the middle chamber. Collectors can apply a sticky substrate in the middle chamber or use an insecticide-treated mesh to immobilize mosquitoes, breaking the life cycle of the mosquito. Collected adults support surveillance of population density and reproductive status. Optimal deployment requires placing traps away from competing oviposition sites. Removing or cleaning nearby containers before installation reduces alternative breeding options and increases trap attractiveness to gravid females. The Procopack aspirator consists of a suction unit, removable collection cup with lid, and an extendable handle for sampling in hard-to-reach areas. It is powered by a portable 9-volt battery, typically carried in a backpack or pouch for mobility. During sampling, the aspirator should be moved steadily left to right at approximately 1 meter per second, with the intake held within 15 centimeters of the surface. After sampling, the collection cup should be sealed before switching off the device to prevent specimen escape. Cups must be clearly labeled with location, date, and time, and stored for later identification or pathogen testing. The CDC light trap operates on a 6-volt power source and uses an incandescent or LED light to attract host-seeking mosquitoes. An integrated fan then draws them into a mesh collection bag for secure retention and later identification or laboratory analysis. Capture efficiency can be enhanced with chemical lures such as carbon dioxide, which mimics host respiration. Human-baited trapping is also possible but requires protective barriers for the human bait. The trap is widely used for surveillance of Anopheles species and other nocturnal vectors and can also collect sandflies under suitable conditions. The fifth surveillance tool on our list is the human landing collection. This technique involves having a trained collectors expose a specific part of their body, most commonly the lower legs, to attract host-seeking mosquitoes. As mosquitoes attempt to land and initiate blood feeding, they are captured using aspirators. The mouth aspirator is a simple tool used for manually collecting adult mosquitoes. It consists of 3 main components: a clear collection tube, a filter barrier, and a flexible silicone tube. When employing human landing collections, the collector must carefully consider several key factors. First, the biting times of mosquitoes, which vary by species. Second, the biting location must be taken into account, as certain species, such as some Anopheles mosquitoes, preferentially bite outdoors rather than indoors. Because of the increased exposure to potential vector-borne infections, particularly malaria, the use of chemoprophylaxis and other personal protective strategies are to be employed. Minimize the likelihood of infection during surveillance activities. Valuable insights into vector ecology can also be obtained through the collection of eggs and larval specimens, which can then be utilized for insecticide resistance assays and other biological evaluations. Field-collected larvae may be taxonomically identified, and their associated breeding habitats characterized to determine ecological preferences and habitat suitability. Understanding the oviposition behavior and breeding site selection of vector species is a critical component in the development of targeted and sustainable vector control strategies. The oviposition cup is designed to maintain optimal conditions for Aedes egg collection. The dark cup contains a drainage hole positioned 1 inch below the rim to prevent flooding and submergence of eggs. This design stabilizes water levels during rainfall or overfilling. The cup is then filled up 3/4 with clean water and lined with a wooden paddle or paper to provide an oviposition surface where eggs can be retrieved easily. Effective deployment requires strategic placement near human activity and positioning traps in shaded and secure locations, maintaining a fixed 1-week exposure period. To conduct larval surveillance, larval dipping serves as the collection strategy for collecting and monitoring of mosquito larvae from both natural and artificial breeding sites. To collect larvae using a larval dipping, identify a potential larval habitat and step lightly to avoid disturbing too much water and surrounding vegetation. Hold the dipper at a 45-degree angle, dip the scoop quickly near the edges and around vegetation to collect larvae. After the dip, count the number of larvae by collecting the larval specimens using a disposable pipette and placing them into a whirlpack bag or vial. Record all observations, including negative dips. Keep the samples cool during transport to protect them from heat and stress. Another vector group of significant medical importance is the tick, capable of transmitting a range of zoonotic pathogens, including the causative agents of Rocky Mountain spotted fever and Lyme disease. As with other vector species, assessing the presence, abundance, and pathogen infection status of tick populations within a community is essential for evaluating the risk of disease transmission. Tick dragging is a sampling technique utilized to collect questing ticks from vegetation and ground cover. The method involves dragging a white flannel or cotton cloth, commonly referred to as a drag cloth, across vegetation where ticks are actively seeking hosts. To assemble a drag cloth, researchers typically use a 1 square meter white flannel fabric mounted onto a wooden dowel or rod and can be pulled by a rope or handle. During sampling, a transect is established within the study area, and the cloth is slowly dragged over vegetation such as grasses and low shrubs, where ticks are likely to be actively questing for hosts. At the end of each transect pass, the cloth is inspected for attached ticks, which are carefully removed using fine-tipped forceps. When establishing a transect for tick collection, linear transects should be positioned systematically throughout the target habitat to ensure representative sampling coverage. The second tick trap on our list is the carbon dioxide tick trap. This trap is a passive collection method designed to attract and capture ticks by utilizing carbon dioxide gas or using dry ice as a chemical lure that simulates host respiration. In the dry ice trap method for tick surveillance, a white cloth or board measuring approximately 1 square meter is laid flat on the ground to provide contrast for detecting ticks. A vented container, such as a styrofoam cup or cooler with perforations, is positioned at the center of the cloth and filled with 1 to 2 kilograms of dry ice. As the dry ice sublimates, it releases carbon dioxide, which simulates host respiration and effectively attracts nearby ticks. To enhance tick capture efficiency, a sticky barrier such as petroleum jelly or double-sided adhesive tape may be applied around the base of the container to capture ticks as they approach. The trap is typically left in place for 1 to 3 hours, after which ticks visible on the cloth are collected using forceps or adhesive tape. Selecting appropriate surveillance tools depends on key factors and study objectives. Tools used must be appropriate for species and must match the behavior and biology of the vector. Anopheles, Aedes, or sandflies each require specific methods suited to their unique host-seeking and breeding behaviors. Environmental conditions such as temperature, humidity, rainfall, and habitat type can influence trap efficiency and introduce sampling bias. Trap design and specificity determines appropriate use. Traps are species-specific and should only be used for their intended targets. Careful consideration of these elements ensures accurate sampling and reliable, meaningful surveillance outcomes. When selecting surveillance tools, researchers face several challenges that can affect study design and implementation. Some tools, such as the BG Sentinel trap, are expensive to acquire and maintain, while simpler options like ovitraps are low-cost but labor-intensive, requiring regular setup and monitoring. Balancing financial and human resources is essential for sustainable surveillance. Methods like human landing collections expose collectors to potential infections. Ethical protocols, including informed consent, protective measures, and chemoprophylaxis, must be followed to minimize risk and ensure participant safety. Long-term studies and large-scale deployments demand careful planning, significant resources, and community cooperation to prevent oversampling or logistical strain. In summary, effective vector surveillance requires balancing scientific goals with ethical standards, resource limitations, and practical feasibility.
Mi nombre es Roberto Barrera, yo trabajo para el Centro para el Control y Prevención de Enfermedades en la división de dengue que se encuentra en San Juan, Puerto Rico. Yo soy el líder de la actividad de entomología y ecología y nosotros básicamente estudiamos los vectores de dengue y otros arbovirus como el Zika, chikungunya, fiebre amarilla y estudiamos la ecología para poder entender mejor cómo manejar estas poblaciones. Yo he estado en el campo de la ecología de mosquitos por muchos años y nos estamos dedicando a entender mejor cuáles son las metodologías emergentes que tienen algún potencial para controlar a aegypti y bajar la transmisión de las enfermedades que son causadas por estos arbovirus. Pues sí, existen nuevos desarrollos interesantes en las tecnologías de muestreo en el campo de insectos vectores. Estos nuevos desarrollos incluyen el uso de dispositivos de captura que se pueden monitorear de forma remota, sin necesidad de visitas frecuentes a las trampas, para contar e identificar a los especímenes. Esto se logra utilizando reconocimiento de sonido o visual, software de inteligencia artificial, bases de datos masivas y telecomunicaciones. Estas herramientas sofisticadas y probablemente costosas serán valiosas para monitorear los insectos vectores en áreas remotas y en áreas urbanas donde las trampas puedan protegerse contra robo o vandalismo. Pues, la principal brecha en los sistemas de vigilancia para el control de insectos vectores y enfermedades es la falta de conocimiento sobre los valores umbrales de la densidad o cantidad mínima de insectos vectores que es necesaria para la transmisión local de arbovirus. O puesto de otra forma, ¿cuál debe ser la reducción en la cantidad de insectos vectores para prevenir la transmisión? Una vez que se identifica el umbral de densidad, se simplifica la vigilancia porque la pregunta no sería ¿cuántos insectos vectores hay?, sino si la cantidad de insectos vectores está por encima o por debajo del valor umbral. Esto también puede simplificar la evaluación de las estrategias emergentes de control de insectos vectores, ya que la evaluación de los resultados del control en términos de la reducción de la enfermedad siempre es un desafío. Tener un umbral validado de insectos vectores ayudaría a los programas de control a establecer objetivos claros del programa y para monitorear su progreso.